You guys and gals all make it through that other homework? The vector stuff. All right, some of those were tough at the end. Feel free to come by. I'd be glad to help you. 12 to 1, Monday, Tuesday, Wednesday, if you want help on that vector stuff. All right, well, let's talk about dot product. This should be pretty easy. This is our last section. So we're looking for, like we already said, So I'll just write it right on here. So we're looking for practice exam. So Monday, this next Monday, whatever that is, the 13th, is our practice exam. Practice exam number 4, and Wednesday will be real exam number 4. Because we're at the end here, we're at 4.4. 4 sections per chapter. This is the last section. So we'll finish today. Monday's the practice exam. Wednesday is the real exam number 4. And then we only got one more after that. The end is approaching. All right. So let's take a look. So the dot product. What does the dot product mean? Let me give you the definition. It basically let me just write it with words, then I'll maybe write some math symbols. Multiply multiply the numbers in front of I plus then multiply numbers in front of I, numbers in front of J, then add. Then add. So that's it. In other words, if you have, let's say, let me give you the official, what it would look like. If you have AI plus BJ, let's say dot, that means dot. So dot product is like a special kind of multiply. Now let me say that first time. What we're doing today is a special kind of multiply. It's not normal multiply. Notice it's not FOIL. We're not going to do what you would normally do for normal everyday multiplication. Remember, vectors are a new creation, right? We're in a new world here, the vector world, right? And we're making up new rules for how you add, subtract, multiply, and divide things. Remember what math does. Math makes up things that help us do things in the real world, right? So math has made up this new thing called vectors. And so whenever you make up a new thing, you got to make up the rules for how you add those things, subtract those things, multiply those things, divide those things, and simplify those things, and other things you do with those things in ways that are useful for real-life applications. See how math works with the real world. They just make it up in ways that are helpful. So they've made up this special way of multiplying, not the normal way of multiplying, this special way of multiplying called the dot product. They actually have another way. They actually have 2 ways of multiplying vectors. We're not going to do the other one in this class. If you go into calculus, you'll learn what's called the cross product, which is something more complex. You need matrices and the whole fancy thing to do those. Anyway, we're just going to do the dot product, which is the most simple way of multiplying. And it basically means, okay, so you got 2 vectors. So the first vector, notice this could be any number times I, any number times j, right? That's the first vector. This is a vector, right? Vector has an I and a j component, sideways and vertical components, right? And then, so let's say the other one is c times I plus d times j. That's just any old 2 vectors, right? So this vector dotted with that vector. What's the result? It's a times b. So that's what it's saying here. You multiply the numbers in front of I. So just take the A. Oh, C. I'm sorry. A and C. Better follow my own rules here. A times C. Add B times D. So you just multiply the numbers in front of I, multiply the numbers in front of J's, and add them together. Now, why in the world would you ever want to do that? That's a weird way to multiply. It's like we did part of the FOIL. We multiplied this with this, we multiplied that with that, but we didn't do the whole FOIL. Right. They're making it up this way. They're saying this is something we find useful, and we'll see why right away. Why this is a useful kind of thing to do. Like I said, there's other ways to multiply. We're not foiling here, are we? They never did do a FOIL way of multiplying vectors. The other way, cross product, is wildly different. It's for 3D, 3-dimensional, and it does other very, very different things. So again, remember, they make up math in ways that are useful for doing things. All right. So anyway, so there you go. So let's actually do this one. So let me go to, now that you got the definition, well, actually, I can squeeze it in right down here. let's just put it in right down here. So they're saying take vector v and dot it, dot product, special way of multiplying with vector w. So here's vector v, 6i plus j, dotted with vector w, which is I plus 6j. They're very similar vectors. That's funny. Anyway, good so far? So this is vector v dotted with vector w, as they told me right here and right here. So they want me to dot vector v with vector w. What is the dot product? You just multiply the two. What number's here? 1, huh? So it's just 6 times 1 plus, and this is 1 times 6. Add them together, 12. So it's very simple to do. It's the simplest kind of multiplication. Notice it's not a vector. It's just a number. The dot of two vectors is not another vector. It's not an ij thing anymore. It's just a number now. We call that a scalar. That just means not a vector, number. It's just a fancy word for number. I don't know why we don't just say number. But for whatever reason, the math world has made up the word scalar. So when they say scalar, when you're in the vector world, and they say, hey, that's just a scalar, they mean it's just a number. It's not a vector any longer. So you notice you dot two vectors and you get just a plain old number. It's not a vector thing anymore. They could have made up different rules. They could have said, hey, multiply the two I things and that'll be your new I. It'll be 6I. And then multiply the two j things and that'll be your new j. And the answer will be 6I plus 6j. They could have made it up that way. They didn't, because it turns out that's not useful for real life applications. So that's not what they did. They said just multiply the I things and drop the I completely. Multiply the j things and drop the j completely. And just add those up and it's just a number. That's what they did, and we'll see why that's actually useful in a second. Pretty easy? Let's do part B. That'd be, well, maybe I can just squeeze it in right up here. That's just pretty easy. So v dot v, so you just take vector v, which is 6i plus j dot itself. 6i plus j dot 6i plus j. What do? Just multiply the x with the x, or the I with the I, whatever you want to call it. 6 times 6, 36. Add, and then 1 with 1. 1 times 1 is 1. 37, done. Good? Easy? All right, so there we go. V dot W, there's V, there's W. So they want me to take vector v minus 7i minus 5j dotted with vector w. So vector v dot with vector w. Oh, yes. See, I did forget. I told you. Yes. All right, we're doing well. Easy enough for you. So you just multiply these two x numbers. Minus 7 times minus 10. Add minus 5 times minus 7. That's 70 plus 30. 100. Boom. Dot product's 100. It's a number. Dot two vectors, get a number. And then v dot v, we can do that. I'm going to move on. So there we go. Questions? Feel free to speak up. Okay, so you want to try that one? So we've got vector u, so which is 3i minus j, vector u, dotted with v plus w. So that's 3i plus j, add w, which is I plus 2j. Right, this is v, this is w, and this is vector u.
I need to put it back real fast because I left my scantrons at home.
Okay, sure.
So,
you want to hand it back here? All right, so there we go. U dot v plus w. We all good? Sure. So how do we carry that out? We have to add the stuff inside the parentheses, right? First, always do the parentheses first, right? So go ahead and combine this stuff first. Add the stuff inside the parentheses there first. So you'll get 3i and 1i is 4i, and 1j and 2j is 3j. Is that good so far? Just add the stuff in that parenthesis. Just do the v plus w. And now go ahead and just do the dot product. From there. So do the dot. And so that's going to be 3 times 4 plus, and then it's what? Negative 1 times 3, huh? What's that? 12 minus 3, 9? And there we go. We good? Easy enough? One of your favorite sections so far? Pretty easy, right? Dot product's pretty simple. If you go on to calculus and you do the cross product, then you'll really appreciate the dot product. Because cross product's a big pain. The other way they multiply is much more difficult. Okay, so they're saying, all right, we got a vector v and we got a vector w, and we want to find the angle between those two vectors. How do we find the angle between two vectors? How do we do that? We could draw them. Let's draw them. It's not really how we're going to solve the problem, but it might be good just to see what we're even talking about. So now remember, vectors they're not anchored. The boat can float. Doesn't have to stay at the dock, right? But nevertheless, it's nice to put them at the origin. It's just convenient. So I'm going to dock them both at the origin. So if you take vector v, and you start him here at the origin, you tie him to the dock, where does he go? 2 to the right, and then down 1, huh? 2i, down 1. So right 2, down 1, boom, there's vector v. We good so far? Right? 2 right, down 1. 2i minus 1j. Okay, now let's do the other vector, which is vector w. Where is he? He's right 2 up 3. That's vector w. Up 3, right 2, this one's down 1. We good? So this one's right 2 up 3, or 2i plus 3j. This one is right 2 down 1, 2i minus 1j. Good, so there's the two vectors, and what we're asking is, what is this angle here? What is this angle between the two vectors? What is it? How are we going to find that? How do you find the angle between the two vectors? Well, first off, let's call it theta. And what we're going to do is, I'm going to give you a little formula. I'm going to give it to you just like magic. Here it comes. The cosine of that angle between two vectors turns out to be the dot product of those two vectors over the magnitude of vector v times the magnitude of vector w. Now, I don't like doing math like it's magic. Like, poof, there it is. So if we have time, maybe today, maybe next week, I'd like to do a proof on that. I'd like to show you where that comes from. Like, how'd they come up with that? So maybe. I don't do many proofs in here. But that might be a good one. It's not too difficult and good to see where it comes from. Anyway, but for now, let's just use it. That's a true fact. Going to be something you want to definitely put in your 3x5 card. The cosine of the angle in between two vectors is always the dot of the vectors over the magnitudes multiplied. So right away we see one of the very great uses of the dot product. It's helpful for finding the angle in between. So all right, so let's carry it out. So in fact, let me move this up. I should have written it up here. So the cosine of the angle in between is the dot product over the magnitude of v times the magnitude of v. You know those double bars mean magnitude, length of, right? How long vector w is, how long vector v is. That's what's going on in the denominator, right? Length of, magnitude of, right? Okay, so let's crank it. Here we go. So so on the top, so the cosine of the angle And at the end, we're going to have to do inverse cosine. That's how we're going to find the theta angle. So the dot product, so that'd be the 2I minus j dotted with the vector w over here, 2I plus 3j. So the dot product of those two. On the bottom would be the magnitude. Well, how do you find the magnitude of a vector?
The square root of
Yeah.
a squared plus b squared.
Right? Remember the magnitude of a vector, like the magnitude of v. How long is v? Well, if you look at this little right triangle, isn't it? It's over 2 down 1. Right? For v, if you want to know the length of v, that's a little right triangle right here, isn't it? A squared, b squared, c squared. That's why the formula for magnitude, the length of a vector, the magnitude of a vector, how long it is the square root of a squared plus b squared. So it's the square root of 2 squared plus 1 squared. And you could call it negative 1 squared if you want. Whatever. Same thing, huh? Right? Square root of a squared plus b squared. That's how you always do magnitude. Remember, that was last night's homework, right? So then the magnitude of a vector would be square root of 5. So the magnitude of vector v, the length, how long vector v is. How long is vector v? Square root of 5. Right? Because a squared plus b squared is c squared. Everybody with me on that? Right, this is c, the length of it. So 2 squared plus 1 squared is c squared. So root it. C is square root of a squared plus b squared, isn't it? That's where that's coming from. Just reminding you again. That's how we find the length, the magnitude of a vector. So that's magnitude of v. So that goes right here. Now we got to do magnitude of w and put it right there. So what's the length of vector w? Same thing. Kind of running out of room here. Let me do it over here. So the magnitude, I don't know where to put it. How about right here? So the magnitude of vector w, the length of w, a square root of a squared plus b squared, 2 squared plus 3 squared, which is the square root of 4 plus 9, 13. So times square root of 13. That's the length. That's how long vector w is. So good so far? So the cosine of the angle in between the two vectors is the dot product over the two magnitudes multiplied, the lengths multiplied. So now we got to finish by doing the dot. Well, not got 2 more steps to go. Let's do the dot product at the time. You know dot product. The I times the I and the j times the j and add them together. Right? So 2 times 2 is 4. Add negative 1 times 3 over square root of 5 square root of 13. What's that? 4 minus 3. It's 1 over the square root. You can just multiply those together, 65. 1 over the square root of 65. I just did 5 times 13, right? Square roots can just multiply. 4 minus 3 made 1 on the top. We good there? So we get to there. So the cosine of the angle in between those two is 1 over the square root of 65. So how do I find the angle in between now? Inverse cosine, huh? Inverse cosine of 1 over the root of 65. So take out make sure you're in degree mode. Take out your handy dandy calculator. Whoops. That's not what I wanted. Where am I? Cosine inverse of 1 divided by, and I'm getting 82.87. I don't know how far they want to round. Round nearest tenth, so 82.9 degrees. 82.9 degrees? We good? It's almost 90 degrees. Looks like it's almost 90, doesn't it? It's not quite 90. Questions I can answer on that one. That all good? Let's make sure. All right, there we go. Let's try that out. So they say, here's V, here's W, find the angle in between V and W. You don't need to draw the picture. That was just for fun. Not required. So just say, okay, the cosine of the angle in between is the dot product over the magnitude of V times the magnitude of W. You can put a dot down below for times if you want, but make sure you understand it's not dot product on the bottom. That's a special kind of multiply, right? On the top, that big dot is a dot product, special kind of multiply. On the bottom, the dot just means multiply the numbers, because these are just numbers on the bottom, aren't they? Magnitude of V, magnitude of V, that's just length. Those aren't vectors anymore on the bottom. All right, so give that a try. Give you a second, see if you can crank that out.
You're gonna trick them.
Is this a trick one?
Yeah.
All right, well, go on and be tricked, or hopefully not. Don't be tricked. I'm surprised too. We'll have to see what the trick is.
You just put 0 for J.
Oh yeah, right, yeah. Exactly. Sorry, right, exactly, totally right. Yeah, V is 2I plus 0J. Right on. Good job. Yeah, when when something's missing, it's just 0. Correct. Because there's no J at all. Right. Good. Good job. So go on from there. Take it from there. Bless you. So the magnitude of vector V is the square root of 2 squared plus 0 squared, square root of 4. 2. Vector V is just 2, the length of it. Oops. W. Mr. Brigham, I have a lot of visitors today.
I thought you were giving a test, but you're actually doing something.
I'm just a quiet lecturer. I don't know if you noticed.
That's
It's a new style.
In contrast to me. I have something I wanted to ask you. I'll ask you later.
Okay. Hey, Craig, actually, I'm glad I ran into you. We're not allowed to do prerequisites now, right? All right, so, magnitude of W, square root of, 64 and 9, 73? 73, 64 and, 73. So, root 73. Good to there so far? You guys are probably already done. You're like, what are you doing, Mr. Aaron? Just crank that thing out. All right. So then cosine theta is multiply. What's that? 6 plus 0, huh? Over 2 root 73, which is 6 over 2 root 73. You don't have to, I mean, you can simplify that and make it a 3 on the top, but you don't have to. Just hit the cosine inverse on your calculator. It's all good. So you can just say, look, I'm not going to simplify it. I'm just going to hit the buttons on my calculator. Theta is cosine inverse of 6 over 2 root 73. I mean, you write it's 3 over root 73. It'll work either way, though. So cosine inverse 6 over... and then the square root. Try these on your calculator because it's easy to mess up, and make sure you're good with them. 69.4 degrees. Y'all getting that? The angle between those vectors is 69.4 degrees. So we start to see why they invented this weird kind of multiplying called dot product. Here's one of the main applications. It's very useful. It's part of how you find the angle between two vectors. That's all they're doing. They're just doing stuff that's useful. Questions on that? Anything I can answer on that? Okay. All right, orthogonal. Now, what is the word orthogonal? Does anybody know that word? Orthogonal?
Equilibrium, right?
Equilibrium? I don't know. Maybe there's other ways it's used in other settings. And in the vector world, it means perpendicular. I don't know why they don't, it's funny how it is, huh? It's funny how they make up new words for the same thing in a new world. They should just say perpendicular. I don't know why they need a new word all of a sudden. But in the vector world, they usually use the word orthogonal. But it just means perpendicular, meaning like one goes this way, one goes that way. Well, it doesn't have to be perfectly straight up and down. It could be like one vector's going like this, and the other vector's going like that. You know, they're 90 degrees to each other. They make a T, in other words, right? It's just perpendicular. It's just what we normally say is perpendicular. So orthogonal means perpendicular. Okay. Think with me, y'all, for just a second. How can I test? Now, I could draw them. Of course, I don't want to, though. I could draw them and try to eyeball it and say, yeah, they kind of look perpendicular. But I might get messed up. I mean, I thought these back here kind of looked perpendicular almost. It turns out they weren't. They were 82.9. They were close to 90, but they weren't quite 90. So I might be wrong doing it that way. So I want some kind of formalistic way of determining if two vectors, v and w, are perpendicular, orthogonal. How might I do that? Remember that think about that formula we just came up with. Cosine theta is the dot product over the magnitude of the first one times the magnitude of the second one. What if the angle between them is 90 degrees? That's what perpendicular means, right? Angle between them, the theta between them is 90 degrees if they're meeting at a right angle, perpendicular, orthogonal. So if the angle between them is really 90 degrees, what will that formula come out to be? What is the cosine in 90 degrees? It's 0, right? Remember from the unit circle, 90 degrees is up here, and that's over 0 up 1. Cosine is the x value, sine is the y. Yeah, right. Good job, guys. Cosine is 0. So what? Well, that means the dot product over the magnitude of v times the magnitude of w must be 0, because if the angle's 90, I mean. If the angle is truly 90, if those vectors are truly at 90 degrees to each other, then cosine of 90 will be 0. So that means the dot product over the magnitudes must be 0. So all we need to do is compute this. If it comes out 0, we know that angle's 90, huh? We know they're really at 90 degrees to each other. Wendy?
Don't you just need to compute the numerator?
Excellent. That's what I was going to say, but I'd rather you say it. Why? How do you know that?
Because anything dividing into 0 is 0.
Well said. Right, yeah. So let's take, so exactly what Wendy's saying is exactly where I was going on the next step. So therefore, I just said, we just got to figure this whole fraction, and if it comes out to be 0, we know they're 90 degrees, because cosine of 90, 0 must be 90 degrees. But even better, like Wendy's saying, you don't even need to mess with the bottom. All you got to figure is the dot product. Why? Well, how does a fraction ever equal 0? What if I said, hey guys, I got a fraction. I got a number over a number, and it's coming out 0. What does that mean? 0 on the top. It means nothing about the bottom. It doesn't matter what the bottom is. It could be 7, 8, 10, 10 million, whatever. 0 over anything is 0. Yeah, so it just means the top is 0, doesn't it? The bottom can't be 0. What happens if the bottom is 0? That's undefined. That's just craziness, right? That's error on the calculator. That's not defined. So that's not what makes it happen. It's the top of a fraction being 0, huh? That's how you make a fraction 0. So really, it all comes down to the dot product has got to be 0. If the dot product is 0, then this whole fraction is 0, which means the cosine of 90 degrees. And the things are perpendicular. So long story short, if you dot them and it's 0, they're perpendicular. If you dot them and it's not 0, they're not perpendicular. The usefulness of the dot product, again. All right, so let me write that out officially. Now that we've arrived there successfully, we've reasoned our way there. So what that means is when v dot w, the dot product, equals 0, they are orthogonal. Let's go with orthog. So that's it. If the dot product is 0, then the vectors are orthogonal, meaning one goes like that and the other goes like that. They meet at theta 90 degrees. So if the dot product is 0, they are orthogonal. All right, so let's test it out. Is the dot product 0 for these two? So here's vector v, which is 5i plus 16j dotted with 3i minus j equals 5 times 3 is 15 plus, and this is what, 16? 16 times negative 1. I'm thinking no, negative 1. It's not 0. So no, those are not, the vectors are not orthogonal. Because their dot product, they want the number, is negative 1. Their dot product's negative 1, it's not 0. Good? So it's a quick, very quick, dot product's quick, huh? Very quick way to know whether two vectors are orthogonal without drawing them or anything. You dot them. So we see again another usefulness of this weird way of defining multiplying. Easy way, but weird way, called dot product. It helps you know right away whether they're perpendicular or not. Good on that? So V equals 4i, W equals negative 5i. So use the dot product to determine whether they're orthogonal. What do you think? If I take 4i, the j is missing, so it's 0, dotted with minus 5i plus 0j, right? This is v, this is w, the dot product. Going to get 4 times minus 5, minus 20 plus 0, minus 20, no. So no, not orthogonal, dot product's negative 20. Easy question. Not only that, which way does that vector go? 4i? 4 to the right. And which way does that vector go? 5 to the left. Right? They're not orthogonal. They're 180 degrees apart, aren't they? They're parallel, actually. And we'll get to parallel in a minute. How can you know if two vectors are parallel? Well, the angle between them's got to be 180 or 0. Well, we'll talk about it more in a minute. All right, so U equals V equals W equals. All right, so 5U dot 3V minus 4W. Find the specified scalar or vector. All right, so let's give it a go. So first off, what is 5u? That just means 5 multiplied by the u vector. Bless you. Good so far? There's 5 multiplied by the u vector. And 3 multiplied by the v vector. And 4 multiplied by the w vector. I'm just going to figure out all the components and then put them together. 4 multiplied by the w vector. I'm just doing these different parts here. 4 times the w vector minus 12j. Okay. Now let's put it all together. So we got the 5u, which is minus 10i plus 15j, dotted with the 3v, which would be this one, 6i minus 3j, minus the 4w, which is minus 12j. Everybody good with that? So that's 5u. This right here is 3v. This right here is 4w. So dotted and subtracted. Good there? Just carefully writing everything out. So we just need to work that out. Minus 10i plus 15j dotted with 6i minus 3j, and then the double negative is going to be plus, as you know, plus 12 would be plus 9j on that. Plus 12 plus 9j. Yeah, 6i plus 9j. Good so far. And so then we do the dot thing. Let's do the dot thing. Minus 10 times 6 would be, and then add 15 times 9. So minus 60 plus 90 and 45, 135. Is it 75? And we're done. Yeah. Good? I go too quick? Questions I can answer? All is well? So did the answer come out to be a vector? They said, you know, find the specified scalar or vector. Did the answer come out to be a scalar or a vector? Yeah, this is a scalar, isn't it? I mean, it's just a number. It's not a vector. Has no more I and j in it, right? All right, so good. All right, so parallel, orthogonal, or neither. So let's first off test for orthogonal. Let's dot the two things, right? Let's dot the two vectors. We'll just start off right there. So I'll take v dot w. So that'd be minus 5i plus 4j dot with w minus 10i plus 8j. Okay, so go ahead and do that. First off, I'll let you do that. First, dot them and see if they're orthogonal or not. So let's do that. It's just coming out okay. So multiply that times that. That'd be what? 50i. What am I doing? No more I. You're supposed to drop the I, huh? Plus 4 times 8, 32, which is 82. So what does that mean? Are they orthogonal or not? Not 0. So they're not orthogonal. Orthogonal. They're not 90 degrees to each other, are they? Good. Dot product's supposed to be 0. Okay, so they're not orthogonal. Let's cross that one off. Are they parallel? How do you know if the two vectors are parallel? Well, I could give you some formula thing like we talked about, right? Cosine of the angle can be 0 or 180, which means the cosine is either 1 or negative 1. We could do that whole thing. But I think it'd be easier, parallel, just look at them. Draw them, put them on the, I think it's easier just to see them. So let's just do this one. Minus 5i plus 4j. So that means back 5 up 4. 1, 2, 3, 4, 5, up 1, 2, 3, 4. Here it is. There's vector v. Back 5, up 4, huh? And w is back 10, up 8. So it's back 10, up 8. So there's vector w. Yeah, they're parallel. Right? See how we know that? Because 10 is twice as far as 5 and 8 is twice as far as 4. It's headed the same way. It's the same slope. Parallel, yeah, does that help? Parallel means same slope. Rise over run. Slopes are the same. What's slope? Rise over run. How about that? Can I do it this way? Which is J stuff over I stuff. So what's the slope of V? The J stuff over the I stuff. 4 over negative 5. 4 over negative 5. What's the slope of W? 8 over negative 10, which reduces to be the same thing. See how that's the same? Same slope. See how their slopes are the same? Rise over run, J over I. Their slopes are identical. So yeah, they're parallel. That's the easiest way. I could give you some dot product formula thing.
The numbers are really big though.
Yeah, even if they're really big, you can just do the two slopes and just reduce them. It'll work for any numbers. Yeah. Yeah, so just find out if the slopes are the same. If the slopes are the same, then the things are parallel. Does that make sense on that? Equal slopes, they're parallel. So yeah, these ones are parallel.
So like basically if it's double that, like if it would have been like with the 5 like 20i and then like
Yeah, if it would have been minus 20i plus what? 16j. Yeah, because again, the y over the rise over the run, then reduce it, divided by 4, top and bottom, back to minus 4/5. Yeah. So just take the slope, rise over run, j over I, and reduce it. If the two slopes are the same, they're parallel. Two slopes are not the same, they're not parallel. Now, the slopes can be exactly the opposite, right? In other words, it could have been going this way. That's still parallel, right? That's still parallel. So what would that look like? The negative would be on the top instead of the bottom. It would be down 4 over 5. So in other words, if the slopes are the same except for sign, they're parallel. Does that make sense on that? All right, so try number 11 there. So, is that big enough? Can you see that? Here, let me make. There we go. So try that one. There we go. Vector V, vector W. Find out. So start with the dot product. Start, there. See if they're orthogonal. Two times 5 plus negative 7 times 6, 10 minus 42, negative 32, not orthogonal, right? The dot product is not 0, so they're not orthogonal. Okay, so that one's, check that one off the list. No on orthogonal. So are they parallel? So now test that. So all I gotta do is rise over run, j over I, j over I. And see if those fractions are the same or negative of each other. That works too, right? So they're not orthogonal. So parallel. How do we determine that? So I would say rise slope, which is rise over run. So for V, the slope is negative 7 over 2. For W, the slope is 6 over 5. Those are not the same. They're not negative of each other either. They're just completely different. So not parallel. So this one's a neither, huh? Those two vectors are neither parallel nor orthogonal. They're somewhere in between. Are we good with all that? Questions on all that? All right, I'll move. All right, so try that one. Vector V, vector W. Start by dotting them, right? 2I minus 7j dotted with 9I plus 18/7 j. So dot them. See if that comes out 0. All right, so when I dot them, 2 times 9 plus -7 times 18/7. Good so far? Going to dot them, the I times the I and the J times J, and add them up. So it's 18 plus. Now what happens when the whole number 7 multiplies the fraction 18/7?
The sevens go in.
Yeah, it's over 1, right? Any whole number's over 1. 7's cancel, it's -18. Yes, it's 0. So yes, orthogonal, huh? Don't even need to look further. Those two vectors are at 90 degrees to each other. The dot product is 0. They are orthogonal. Is that good? So this dot product thing, I was just doing it a month ago with my daughters in Calc 3. It doesn't go away. It keeps, this dot product and orthogonal and the cosine theta formula. They keep using it and using it and using it. Calc all the way up the line. All right, I don't know if you can read all those words. I can't really blow them up because it goes off the screen. But so this is physics. We're doing a physics application. Work is force times distance. Work's an official thing that's measured in the world of physics. So the work done in moving something over a distance is the force required times the distance that you move them. I'll say if the force is the same line as the movement. That is. So in other words, what am I talking about? If I take this calculator, well, here, let me do my book. It'll slide more easily. So if I take this book and I slide it along the table, I just did some work. I applied some force and moved something over a distance. You could calculate how much work is done. So, whereas if I push on this wall, I'm exerting some force, but nothing's moving. So there's no technical work being done, even though it could take some work, from me, some strain or whatever, but officially the work done is nothing. Nothing was accomplished. Why? Because the distance is 0. So the force times the distance is 0. This wall didn't move. So that'd be 0 work in the end, right? So force times distance is work done. This is how they calculate all kinds of things, all kinds of real-life applications when they talk about the work that a car does in moving something down the road. And, this opens the door to all kinds of very important calculations used in the world of physics. So, force times distance is the official definition of work done. Now, why do I say if it's in the same line as the movement? Well, I could move this book by pushing straight in the direction it's moving. Then it's just however much force I'm applying times the distance. Great. But I could also move this book by going like this. I'm going to push down really hard and a little bit of an angle, and it'll kind of move. Now, I'm wasting a lot of my force, aren't I? Because it's not all, my force is kind of at this angle, and the book is moving at that distance. The two vectors are not aligned, are they? So my force vector and the distance, the movement vector, are not lined up. Whereas when I came down here and just pushed it straight, then my force vector is lined up with my movement vector. And so you just need to multiply force times distance just straight out. That's what I'm saying. If the force and the movement are lined up, they just multiply them. Boom, you got it. If I'm pushing with half a pound of force, doesn't even feel like half, maybe quarter of a pound of force. So if I'm pushing with a quarter of a pound of force and I move the thing, 1 foot, or let's say 2 feet, I move it 2 feet, you'd multiply those together, they come out 0.5 foot-pounds. They call that foot-pounds. That's the English units for work. So half a foot-pound of work. I did that much foot-pound of work. But what if I'm taking this thing and I'm pushing down, kind of like at this angle, and moving it like that? Well, there was a harder force applied, but it wasn't all lined up, was it? Part of it was lined up, it wasn't exactly lined up. So you can't just say, well, now you're doing more work. Actually, it's the same work accomplished. Because as I push like this at an angle, there's a component of my force vector. My force vector is at an angle. There's a component that's sideways and a component that's down. Remember how we break vectors into the two components? Sideways component, vertical component. So the sideways component is actually the same as when I just pushed straight sideways. How you sort all that out, what is very convenient for sorting that out, is the dot product. That's why we're bringing it into play right now. So work. Now I just told you here it's force times. This is just normal multiplication. Let's just say times like that. That's just normal. You can just use numbers. Like I said, a quarter pound of force. If it's lined up times 2 feet of movement, 0.5 foot-pounds of work is accomplished in moving that. But what if I push? You don't normally your force is not always lined up exactly with your distance, your movement. What do you do in that case? You take the force vector, that's a vector, and you dot it. That's the dot product with the distance vector. And this is no matter lined up or not. So that's the one we really use, because the dot product takes care of the lining up or not lining up as the case may be and makes it all work out. I don't really have time to prove all that, but it does. So that's why we use the dot product, because if they're not lined up, if I say, well, I'm pushing down with like 30 pounds of force, but I'm only moving the thing, so do I go 30 times 2 feet? No, because not all that force is lined up, right? Well, then how do I do it? I got to figure my force vector and my distance vector and dot them. That will always work. So this is the formula we always use for work in physics, the dot product of force and distance. Okay, so let's go back then to the problem we're looking at and say, all right, so what's being done here? A wagon is pulled. So we have some ground. We have this wagon. I'm going to draw a wagon, which is always a challenge for me. And the wagon, at what angle? 45, okay. So kind of a long handle. So here's the handle. Let's see, I can't draw. I'll just going to stop like that. There we go. So there's the handle, and here's the person. They are pulling the wagon. Hey, that's not bad for me. All right, they're pulling the wagon. They're walking that away. Now, notice the angle of the force. 45-degree force vector. This vector here is the force vector. Let me just put the F there. That's the force vector. Let me change the color. So there is they're pulling. Sometimes they're not stooping down and pulling the wagon, the handle right in straight line with the ground, are they? If they wanted to stoop way down, you know what I mean by that, right? If they wanted to stoop way down and pull the handle straight, they'd have to. I can't draw a person bending down, I don't think. I'm going to draw a short person. So a really short person could maybe do that. A child maybe could pull it straight. Then the force vector would be exactly in line with the distance vector, because the movement is this way, right? The distance vector is straight to the right. So does everybody see what I'm talking about? So the distance vector, so how's the movement happen? What's the wagon doing? It's moving that way, straight to the right. Now remember, that's the distance vector. Remember, it doesn't matter where I put that vector. I can put that vector up here. Remember, they're a boat that's not anchored. I can put it over here. I can put it over here. I can put it over here. All that matters about the vector is how long it is and what angle it's pointing at. It's a road sign. Remember, the boat's not anchored anywhere. Doesn't matter where I draw. So don't get hung up on that. Don't think, wait, why'd you draw it here and not there? Remember, I can put it over here. Boop. As long as it's straight to the right, however long it is, that's all that matters about a vector. Not where it sits. We don't care where it sits. It's just its direction and its length. Took me forever to get that straight. So that's all that matters. So the distance is straight to the right, the distance vector, because why? Because the wagon is moving straight to the right. The wagon's not going up. Wagon's not going down. Wagon's going straight to the right. And the force vector is at an angle, though. So the force vector is not perfectly lined up with the distance vector unless you got a super short person, a child, pulling the wagon. Then the force vector would be lined up with the distance vector. That's not typical. So let's say that's not the case. So, all right, so how do we find the work done in pulling the wagon? Well, we got to find the force vector and the distance vector and dot them, don't we? So the work will be the dot product. So let's find before we get there, let's find the force vector. So how do we find the force vector? They're pulling with 40 pounds of force. 40 pounds of force at an angle of 45 degrees. So in other words, they're going at an angle of 45 degrees with the horizontal. They're pulling with 40 pounds of force. That's what this person is doing right here with their hand. They're pulling with 40 pounds of force at an angle of 45 degrees. So I got to make that vector into like an IJ thing. How do you take a 40-pound at an angle of 45 degrees and make it something I plus something J? That's what I got to get for that force vector. Got to make it into an IJ. How much sideways? How much up? How much I? How much J? How much sideways? How much up? How do I do that? Remember what we learned in last night's homework about what you do? The sideways component is always cosine, and the vertical is always sine. Remember? X is always cosine, Y is always sine. So in other words, the way you turn any vector into an IJ thing, the force vector will be the magnitude of the force, which is just 40, times the cosine of the angle, plus the magnitude of the force, 40 again, times the sine. Oh, and this should be I, and this should be J. Remember that formula we did in last night's homework? So that's all you got to do. So the force vector will be 40 cosine 45 degrees I plus 40 sine 45 degrees J. So if they give you the angle with the horizontal, you just go, all right, I can make that into IJ, just 40 cos I plus 40 sine J. It's always that way. Why? Because cosine is always x. Remember the unit circle? Cosine is always sideways, huh? Cosine is always x value. Sine is always y value. Right? See how all those things tie together? So there's your force vector. Do they want exact answer or they want round and there's whole number? Yeah, so we can just use our calculator on that. So, you guys have your calculator. What is 40? Because you guys know the cos 45 is root 2 over 2. We'll just get a decimal though. So 40 times cos 45. What's that? 28.28. They want a whole number in the end, so I'll go, remember, use a little more accuracy when you're in the middle of the problem still. So let's use 2 places, maybe it's good enough. 28.28. I, and then the other one's going to be the same, huh? 28J. Because it's at 45 degrees, it's the same side as up. It's perfectly diagonal. You guys good so far? I got the force vector. scribbly here. So that's always how we get a vector. Whenever they do something at an angle, we just do cosine of the angle times I, sine of the angle times j, multiplied by the magnitude. So there we go. It's 28.28i, and I'm using 2 decimal places because they want a whole number in the end, so I'm using a little more accuracy because I'm still in the middle of the problem. So there's the force vector. What's the distance vector? Well, yeah, they're going 80 feet straight to the right. The distance is 80 feet straight to the right. So what's the distance vector? 80i. Straight to the right. No j at all. No up, down at all, huh? See all the different distance vectors I drew? They're all straight to the right, aren't they? And their length is 80. They're 80i. They're 80 to the right. No j component at all. Make sense? So there's the distance vector. Here's the force vector. So what's the work done now? We're ready to do it. So the work done is the force vector dotted with the distance vector. So it's the 28.28i plus 28.28j dotted with the distance vector, which is 80i plus 0j, really, huh? If you want to put in that 0j there. So this is force. This is distance. We're dotting them. So how do you dot? What's the dot product? You know it. You just go the I times the I and the J times the J and add them up. So it's 28.28 times 80 plus 28.28 times 0. So that's just 28.28 times 80, huh? Times 80, I'm getting, what, 2262.4, so I'll just leave it there. 2262, that's in foot-pounds. 2262, that's how much work is done by that person in pulling the wagon 80 feet. 2,262 foot-pounds. That means pounds times feet. Right? Foot-pounds of work. Luke?
Could you enter that in on Math Excel?
Oh, yeah. Good. Other questions on that? Yeah, so use a lot of accuracy. You can use the root. Yeah, this is root 2 over 2, right? If you wanted to use that, you'd be exactly right. You'll have no problem at all with the rounding in the end. But if you're going to use decimals like I did, you better use, I guess, 3 places past the decimal to get it right to the whole number. Good? All right. Okay. Force of 80 pounds on a rope is used to pull a box up a ramp inclined at 10 degrees from the horizontal. The figure shows that the rope forms an angle of 33 degrees with the horizontal. How much work is done in pulling the box 28 feet along the ramp? Interesting. Okay. So we're pulling this box up the ramp. 28 feet. All right, let me give you a try. So you know the formula. Work done is the force vector dotted with the distance vector. So the whole job really for you is to find the force vector and to find the distance vector. That's the work, right? Because the dot products snap, right? The hard part is find the force vector, find the distance vector. And you know what to do. Remember, it's just for each of those, it's just cosine. You know, it's just the cosine of the angle times I plus the sine of the angle times j. The angle they make with the horizontal. So look at that force vector, and then times the 80, of course, right? The force vector is 80, and what angle does it make with the horizontal? Well, 33. And the distance vector is also not straight to the right, is it? The movement will be up 10 degrees. So how do you find the distance vector? Same thing. Cosine of 10 degrees I plus sine 10 degrees j. You're just going to have to do it for the distance vector also. Do you see that? Because the movement is not flat. It's not straight. Times 28, because the box goes 28. So give that a try. See if you can get that. Give you a second. Okay. So force, they're giving me the force, they're just handing me the force vector. I don't have to work for it. 6I plus 7j. There's the force vector. And it's moving, the movement, the distance, the movement is from negative 4, 2 to 2, 6. Negative 4, 2 to 2. So you're applying a force, there's the force vector. And the thing you're moving is moving from negative 4, 2 to 2, 6. So we really need to draw a little axis system, don't we? And take a look at that. So back 4, up 2. There's the first dot. It's going from there to the point over to up 4, 5, 6, over to up 6, isn't it? So here's the distance vector. Like that. There's the distance vector. So we've got to figure out the I and the j components of that distance vector. Does that make sense on that? The I and the j components of that distance. So how far to the right and how far up, what's the I, what's the j for that distance vector? So can we do that? So how far is it to the right? It started here. It ended here. So how far to the right? 6, right? We good? Starting at negative 4. Getting all the way to positive 2. 6 jumps to the right. Right? 1, 2, 3, 4, 5, 6 to the right. So that's 6I. 6I. Thank you. And how far up is the thing? Goes up, what is it? 1, 2, 3, 4. Yeah, up 4j. Yeah, from 2 to 6, huh? From 2 to 6. Yeah, from 2 to 6, up 4. So it's 6 to the right, 6I, 4j. 6I plus 4j. So that means the distance vector is 6I plus 4j. Is that making sense there? How I figured that out? Just putting those 2 dots. Just counting right and up. And so now, how do we do the work? We just dot them, huh? The work is force dot distance. So you just multiply these two. 6 times 6. Multiply these two. 4 times 7, add them up. So what is that? I was going to say 12. 36, they're multiplying. 36 plus 28. 30, 96, 90, 94? 94, whatever, I don't know what the units are. Dogs. 94 dogs. It's just foot-pounds again. Okay, yeah, foot-pounds. 94 foot-pounds. There we go. Is that good? So we just had to find the distance vector.
It's 64. The 36.
Oh, yeah. I'm just really not adding well today. Thank you. 64. Thank you. 30 BC. Yep, 64. That better? So, yeah, so you just had to find the distance vector yourself by using the coordinates. It's all about getting that distance vector. 6I, 4j. All right, one more. I move on. Okay. Nicole. So they're saying the force is 3 pounds at 48 degrees to the horizontal. So it's at an angle of 48 degrees. That's the force. And the distance, the movement, goes from 4, 6. Oops, kind of scribbly there. The distance goes from 4, 6 to 7, 10. 4, 6 to 7, 10. So you got to get both vectors, huh? It's all about get the force vector, get the distance vector, and dot them. And you'll have the work. So the force will be 3 cosine 48i plus 3 sine 48j. Good for the force vector. Same old kind of thing, right? Whenever we have the angle with the horizontal, this is cosine theta times I, sine theta times j. So we got that. And now, what are we going to do for the what are you going to do for the distance vector? Go ahead and draw the coordinates, huh? Just want to draw the coordinates. Or you can just look at it. If you don't need to draw it, if you can just look at it. How far from 4 to 7? 3. So that's 3i, huh? Because those are the x values. How far from 6 to 10? Plus 4j. There's the distance vector. Good enough? You can draw it if that helps. They made those numbers kind of easy, so I could just look at it. So there's the distance vector, and you know what we're going to dot these two, which means the x times the x. So that'll be 3 cosine 48 times 3 plus, and then 3 sine 48 times 4. So there's the work done, whatever that comes out to be. Use your calculator. So it'll be I'm getting 14.9. They want it round 100. Oh, 14.94. 14.94 foot-pounds of work done. We good with all that? Questions I can